This presentation will provide an overview of the basic concepts of remote sensing in the thermal infrared portion of the electromagnetic spectrum. One of the most exciting areas of remote sensing is the detection and analysis of objects and phenomena based on their emitted energy. Through thermal infrared remote sensing, we are able to see an object's heat and take its temperature. We can use thermal remote sensing to fight fires, placing timely, smoke-free images of a fire's location directly into the hands of firefighters and other emergency personnel. We can also use thermal remote sensing, coupled with innovative technologies such as unmanned aerial systems, to more efficiently study natural phenomena such as the migration of waterfowl. Thermal remote sensing also allows us to take the temperature of our planet and better understand our changing climate. In this lesson, we will take a look at the science and technology behind our ability to study objects based on their thermal properties. Thermal imaging technology is frequently used in things that apply to our everyday lives. Doctors use it to help diagnose disease and general health conditions. We can look at the energy efficiency of our homes by seeing where cold air is entering or where insulation is poor. It is used by building inspectors to detect faulty wiring. Firefighters use it to detect fire obstructed by smoke or walls. All objects with temperatures above absolute zero emit electromagnetic energy. Thermal energy is emitted in the 3 to 14 micrometer range of the electromagnetic spectrum, referred to as the thermal infrared. It is invisible to our eyes but can be detected with thermal sensors. Objects vary in the way they store and emit that energy. That allows us to differentiate between them. Because their thermal emission properties are predictable, we can also derive their temperatures. Thermal remote sensing can thus be simply defined as detecting and recording information about an object in the thermal infrared region of the electromagnetic spectrum. Note that the thermal wavelengths are much longer than those in the near or reflected region of the spectrum. All wavelengths can be said to have temperature. That was demonstrated as far back as the early 19th century. The relationship among objects, emitted energy, and wavelengths can be described by some basic thermal radiation laws. We will start with the concept of a black body and follow 3 radiation laws to understand the relationships among energy, temperature, and wavelengths. A black body is a theoretical concept of a material that absorbs all the radiation that falls on it and in turn radiates energy at the maximum rate possible. It can be described as the perfect emitter. No real objects are true black bodies. However, we can consider the Sun as a black body that emits energy at 6,000 degrees Kelvin, or about 10,000 degrees Fahrenheit, and the Earth as a black body that emits at 300 degrees Kelvin, or about 60 degrees Fahrenheit. 2 radiation laws, the Stefan-Boltzmann law and Wien's displacement law, are used to quantify the amount of radiation exiting a body and its dominant wavelength. Energy emitted from a black body is proportional to the 4th power of its temperature. Actual energy emitted is computed based on a formula expressed in the Stefan-Boltzmann law. Using this equation, we can see mathematically that the energy of our 6,000 degree Kelvin Sun far exceeds the energy emitted by our 300 degree Kelvin Earth. Energy is described in watts per square meter. So we can see the scientific basis of the obvious fact that hotter objects emit greater amounts of energy, very useful if we want to design sensors to detect and measure thermal radiation. Through another law, Wien's displacement law, we see that there is a relationship between the temperature of an object and the dominant wavelength of its emitted energy. The hotter the object, the shorter the dominant wavelength. Note that the dominant wavelength of our very hot Sun corresponds to the visible portion of the electromagnetic spectrum. Our eyes have evolved to take advantage of the wavelengths associated with the Sun's emitted energy. The much cooler Earth emits energy in the far infrared wavelengths. With knowledge of the dominant wavelengths associated with different temperatures, we can design sensors to detect and measure the thermal properties of features. A typical forest fire might burn at 800 degrees Kelvin. Using Wien's displacement law, we can determine that the dominant wavelength is 3.62 micrometers and therefore design our sensor to detect features in that wavelength. Likewise, if we are interested in Earth features such as soil, rock, and water, we know that the Earth's background temperature is approximately 300 degrees Kelvin. We can then apply Wien's displacement law to see that the Earth's dominant wavelength is 9.67 micrometers. Our sensor can then be designed for an appropriate range of wavelengths for sensing Earth materials. Finally, we know through Kirchhoff's law that materials that are good absorbers are good emitters, and materials that are highly reflective are poor emitters. Through the application of additional radiation principles, we can determine the emissivity of real materials, sometimes referred to as gray bodies, and modify the Stefan-Boltzmann law to estimate the temperature of an object using a thermal infrared sensor. We'll now look at a few thermal infrared sensors and how they have been applied. To detect very small fires radiating at relatively high temperatures, the U.S. Forest Service uses the Phoenix sensor, which detects energy in the 3 to 5 micrometer band. It can detect a heat source smaller than a basketball and only 100 degrees Fahrenheit above the background temperatures from 10,000 feet altitude. Here are some examples of Phoenix images. Image interpreters receive extensive training and must meet qualification standards to create these products. Sandhill cranes at Monte Vista National Wildlife Refuge were imaged using an RQ-11A unmanned aerial vehicle mounted thermal infrared video sensor. This sensor operates in the longer of the thermal infrared wavelengths since the temperatures of living creatures are relatively cool. The cranes show up well against the background temperatures of their roosting sites. Imaging takes place at a time when the temperatures of the cranes will be different from that of their background. Many airborne and satellite sensors operate in the longer of the thermal infrared wavelengths. These are used to identify and analyze phenomena such as ocean temperature, geologic features, and pollution studies. Landsat 8 carries a thermal infrared sensor that works in this region of the thermal infrared. Earlier versions of Landsat also had thermal sensors. The image on the left shows the intense heat of a volcano as well as its smoke plume. The image on the right shows the Phoenix, Arizona area, highlighting the darker tones of the relatively cool water and agriculture areas. NASA's MODIS, or Moderate Resolution Imaging Spectroradiometer, covers wavelengths across the entire thermal infrared spectrum, making it useful for both fire detection and for analyzing properties of objects in less extreme temperature ranges. NASA develops monthly sea surface temperature products using MODIS thermal bands. The U.S. Forest Service uses MODIS to detect active fires, issuing GIS-ready fire detection data. Though we cannot see thermal infrared radiation with our own eyes, through an understanding of some basic thermal radiation laws, we can determine the thermal properties of objects and use imaging technology to view and measure features based on their heat signature. We can then harness this technology to learn more and make better decisions about man-made and cultural features in our landscape.